Hello, I am Stefan, a student of Paolo Ienne from EPFL, and today I will present our joint work with our colleagues from IMEC, Francky, Catthoor, and Zsolt, Tőkei. In this picture here, we can see metal stacks of several different technology nodes, and one thing that is particularly obvious is the diminishing cross-sectional area of the wires. This is especially true for the lowermost metal layers. Now, with the help of some elementary physics, we can see that this decrease in cross-sectional area is going to cause an increase in wire resistance, which will in turn increase the delay of the connections. Now, it is pretty easy to qualitatively reason about these effects, but it's a little bit more involved to quantify them and to see how they change the decisions that enter the design of the next generation FPGA architectures. Before we dive into developing models that will allow us to do this quantification, let us first turn to one particular example that should provide further motivation to why we may want to do that. In this picture here, we can see two FPGA tiles with the delays of the characteristic connections annotated for technologies representative of the commercial 16 and the 7 nanometer nodes. We can see that with the reduction in the cross-sectional area of the lowest metal layers, the delay of the intracluster or the local connections, as we call them in this paper, increases quite a bit. Whereas at the same time, the delay of the global or the intercluster connections actually decreases. This is because the pitch of the upper metal layers reduces less dramatically, and then the dominant effect is the reduction of the wire length due to the area scaling. Finally, because the device performance continues to increase between these two technology nodes, the delay of multiplexing also reduces a little bit. Now, given these numbers, it is quite reasonable to ask whether it doesn't become faster to connect two lookup tables in two adjacent clusters than it is to connect two furthest lookup tables in the same cluster. Of course, this would be quite contrary to our usual assumptions when designing, for instance, a packing algorithm. The purpose of this paper is to develop models that will allow us to precisely quantify these effects. The rest of the presentation will proceed as follows. First, I will say something about the metal stack models that we use in this work. After that, I will comment briefly on the area and wire length models, and that will allow us to finally say how we measure the delays of different connections. Here I will also report some initial results, which will then motivate the final study, which is exploring again the optimal cluster sizes across different technology nodes. The first thing that we need to do is to determine at which metal layers we are going to trace which wires of the FPGA tile. In this work, we use two different layer groups with two different pitch options, which typically correspond to the two tightest pitch options allowed by the foundry. We use the lower group for tracing the intracluster or the local wires, which include the wires between the lookup tables in the same cluster, which we call the cluster feedbacks, or the wires from the connection block outputs to the inputs of the cross-parent for the lookup tables. We call this layer group MX. On the upper metal layer group that we call MY, we trace the intercluster or the global wires, which are actually the channel tracks. All right. Now, the most important thing that we need to know in order to be able to calculate the resistance and the capacitance of the wires is the cross-sectional geometry. All the quantities that are necessary for this are shown in this picture here. But unfortunately, the only one that is typically available from the foundries in open literature is the pitch. And for this reason, we derive all the others from the pitch, with all the conversions and the justification for them available in the paper itself. Because the quantity that is the most impacted by scaling is the resistance, as it depends both on the reduction of the thickness of the wires as well as their width, we decided to adopt a fairly recent model for resistance introduced by Tőkei and others, and we simplify it slightly by assuming that there is no tapering of the wires, but that their walls are straight as in the picture above. With this, we obtain the formula that is displayed at the bottom of this slide. Plugging in representative pitches for all the technology nodes considered in this work, we can see on the left first the scaling of the cross-sectional dimensions of the wires, and we can see that they do really reduce as we anticipated in the first slide. While on the right we can see what is the effect of this diminishing of the wire dimensions on the resistance. What is particularly interesting is the high rise in the resistance as we approach the most scaled nodes, which are in this case the 4 nanometer and the 3 nanometer ones. And we can see that the slope of the curve is even much more dramatic than what we could perhaps expect by seeing only the left figure, which shows the dimension reduction. To further emphasize this difference, we also display in green line on the right the classical formula for resistance that we used in one of the first slides. And we really can see that not only the absolute values of the two curves differ, but also their shapes, which illustrates why we want to use the more up-to-date models, as otherwise any effects might even go about unnoticed. Because the 3 nanometer node has a particularly large resistance at the MX layer, we also explore another possibility for this predictive node, which is to increase the thickness of the wires without increasing the pitch, which allows us to trade off some of the resistance of the wires for the increased capacitance. Moving on to the MY wires, we can see similar trends with diminishing cross-sectional area, which causes in turn an increase in resistance, although it is a little bit less dramatic than what we have seen before. And again, because the 3 nanometer nodes can be quite resistive, we explore two different options, where the first one has a fairly tight pitch of 48 nanometers, and for the second one, which we want to explore as a more high-performance option, we move a little bit up in the metal stack and allow a more relaxed pitch of 80 nanometers, which of course comes at an expense of reduced channel bandwidth or capacity. Now, capacitance is much less sensitive to scaling than resistance, and this we can easily see by observing the simple formula for the parallel plate capacitor. Of course, as the distance between two neighboring wires shrinks, the capacitance is going to rise, but because of the dimensions of the sidewalls of the wires also being reduced, this is going to cancel the previous effect, and hence the capacitance is going to be more or less stable. For this reason, we adopted the model introduced previously by Wong and others, which is a little bit older than the one used for resistance, having been introduced in the year 2000. We use it in the form as it appears at the popular PTM website. All right, now that we know how to calculate the resistance and capacitance of wires per micrometer length, we also need to know the lengths of wires in order to be able to measure their delays, and for this we need fairly precise area models. Besides this, the area models are also necessary for determining the maximum number of tracks that can fit into routing channels above the FPGA tiles. Unfortunately, the models that are typically used, which are based on counting transistors, are not really precise enough for scale technologies where even seemingly minor differences in wire length can have substantial influence on their delays. And moreover, these models have even been shown to suffer serious inaccuracies for older planar technologies. For developing the new area models, we start from a floor plan that is fairly similar to the one used by the Stratix architectures, where we have lookup tables stacked in one column on top of each other towards the right of the tile layout, whereas the multiplexes are then stacked next to the lookup table, starting from the crossbar multiplexes, then proceeding to the connection block multiplexes, and finally ending with the switch block multiplexes. Similarly to the edge-lex architecture, we design the switch pattern and the local interconnect pattern in such a way that the number of multiplexes is the same for all of the lookup tables, which allows easier positioning later. Okay, let us now turn to the layout of the lookup tables, because the whole floor plan is centered around them in this case. We adopt a layout model that is similar to the one introduced by Abu Sultan and Catthoor, where we assume that the SRAMs of the loot mask are arranged in an array, and that immediately below there is a decoder tree. We assume that the entire width of the lookup table is determined fully by the loot mask, because it allows ample space for increasing the drive strength of the decoder transistors if necessary, and hence we obtain a completely scalable layout model that depends only on the fin pitch and the gate pitch, which are usually available openly from the foundries. Okay, proceeding now to the multiplexes, we assume that all of them are designed based on transmission gates, as is the case in the edge-lex architecture, And then we used the result of Chiasson, who showed that transmission gate-based multiplexes can have minimum drive strength in the transmission gate transistors, even in planar technologies. With this, we obtain the following layout, which is again completely scalable and depends only on the fin pitch and the gate pitch. Alright, now that we know what are the dimensions of different lookup tables and multiplexes and where they are positioned, we can approximate the routing as a simple rectilinear tree and then run the SPICE simulations to obtain the final delays of all the necessary connections. In this picture here, we can see the delay of reaching from the output of one lookup table all the inputs within the same cluster that are reachable through a 50% sparse cross-spur. And we compute this for all the considered technology nodes. If we focus first on the oldest technology node, which is the 60nm one in this case, we can see that everything is pretty much in order. So the curve is not really dependent too much on the distance traveled to the target lookup table. As we move to the more scaled technology nodes, however, we can see that with the increasing distance to the target, the delay increases by a large amount, eventually even approaching the delay of the lookup tables, representative delay of the lookup tables in the same technology. And for the most scaled node, which is FPGA in this case, the delay of reaching the most distant lookup tables is even surpasses this delay of an individual 6-input lookup table in the same technology. Let's now focus for a moment at the 4nm node, which is the first one in the sequence where this effect of increased MX resistance triggers the very large increase in delay as we try to reach further lookup tables in the cluster. We could expect that introducing some repeaters in these long vertical lines is going to mitigate some of this delay issue, and this really is the case, as we can see in the green curve on the left. However, here we assume that it is possible to center the repeaters exactly at the long vertical line, which is of course not really the case always, because that would prevent routing the wires at a very tight pitch. What is a little bit more realistic is to lay out the repeaters closer to the lookup table output, where the triangular shape of the lookup table allows enough space for that. And here we can see that most of the gains due to the repeaters are largely gone. There's a third option, however, and this is to increase the thickness of this long vertical line by raising it to one of the MY layers. And here, as you can see, this large dependence on the distance traveled is mitigated for the most part, and the delay to the most distant lookup tables drops significantly. So we could even perhaps say that this is a solution, so we just raise all the wires, but we must see what the price for this is. And of course, in order to be able to have any gains, we would need to raise all of the feedback connections in the cluster. And not only that, we would also need to raise all of the more numerous wires from the outputs of the connection blocks to the inputs of the crossbar, because each of them induces a delay penalty on any connection that enters the cluster from the global routing. When we combine these two groups of wires, in the case of the architectures explored in this work, this represents about 20% of the available capacity in the vertical channels at the MY layers, which is not something that we can waste that easily. Of course, with the more complex industrial architectures that would have larger clusters with multi-output lookup tables, the problem would be even larger. But if we focus again on the curves, another solution might suggest itself. We can see that in this short range of, say, 1 to perhaps 2 lookup tables, the MX layers are more performant, or at least as performant as the MY layers, because of their lower resistance. As we go further away in the cluster, of course, the MY layers become relatively more performant. But then, if we had smaller clusters of, for instance, 2 or 3 lookup tables in size, we could achieve the following. So the short span connections could stay local to the cluster, thus being traced at the more appropriate MX layers. And if we want to reach further lookup tables, we could simply exit the cluster, use the global routing at the MY layers, and then enter another cluster to reach the destination lookup table. Now, combining these two curves in the regions where each of them is optimal, we can obtain a curve that is pretty similar in shape to the one that appears in the Agilex paper. And if we take a look at one of the major modifications in the local interconnect that was introduced in this architecture, we can see that the monolithic local interconnect has been distributed into different small parts that cover about 2 to 3 lookup tables in size. And this is qualitatively pretty similar to what we just showed with using smaller cluster sizes instead of the bigger ones. And this serves as a motivation for our final study in this work, which is exploring again the optimal cluster sizes for all of the technology nodes that we consider here. We explored cluster sizes of 2, 4, 8, and 16 6-input lookup tables. In order to be fair in comparisons, we also perform a limited exploration of the channel compositions. Well, to be realistic and similar to the industrial architectures, we also redesigned the switch patterns in order to be more appropriate for the high resistance of the lower metal layers. Finally, we use MCNC benchmarks for all experiments and perform all experiments in VTR version 8. There are further details in the experimental setup, but these are available in the paper. This picture here, we can see the results of the geomean routed delays of all the benchmarks across all technology nodes. And we can see that in the older technologies up until the 5nm one, nothing really strange happens. The cluster size 8, which is still typically considered to be the optimum, is at least of this range, is either the best performing or very close to the best performing one. But as the resistance of the technologies increases, we can see that the much smaller cluster size 2 actually exceeds the larger clusters of size 8 in performance, which is something that we anticipated a few slides back. What is also interesting to see is how the evolution of the most performing architecture performance actually proceeds. And here we can see something that is maybe a little bit worrying, and this is that not only that as technologies progress, the performance gains might be lost, but actually the performance of the more scale technology nodes might become inferior to the performance of one of the older technology nodes. In this case, the 4nm and the 3nm node perform worse not only than the 5nm node, but even the 7nm node 2 generations before. Even if we take the more optimistic version of the 3nm node considered here, which is the F3B, we can see that the increase in performance decelerates a little bit when compared to the previous generations, and this may raise further concerns whether it will be viable to move to a new technology node without substantial architectural changes. We must also comment on why the F3B node is so much better in terms of performance than the F3A. And the answer is in the more relaxed MY pitch. It is 80 nanometers as opposed to the 48 used previously. Of course, this has an effect on the capacity of the channels in the FPGA architecture. And if we take a look at the architectures considered in this work, we can see that the reduction in the channel capacity even approaches 40%. Unfortunately, exploring what effect this has on routability of the architectures went beyond this work, and we leave it for the future to assess this. To conclude, in this picture here, we can see the historical sequence of different technology nodes, and we can roughly label academia in this region here. So between 65 nanometers and 22 nanometers planar technologies are the nodes that have been explored in recent academic studies. Of course, industry has been now for quite some time in the more advanced FinFET region, even including the 7 nanometer. In this work, through this study of the optimal cluster sizes, we try to show that it could be quite interesting for academia to move on to newer technology nodes, because many of the long-standing rules of thumb might start breaking, and there could be quite a lot of space for reinvention of the FPGA architectures. At the same time, we provided models of metal stacks that are appropriate for studying these deeply scaled technologies, which we hope will be useful for the entire community to successfully enter the unknown future, which may not be so obvious at the moment as we saw a couple of slides back. With this, I would conclude. All the source code used in this study is available at the following link, and I would also like to thank Mr. Satwansingh for all his help during the artifact evaluation process, which greatly increased the quality of the repository linked below. Thank you for your attention.